Look at this building. Award-winning design, world-famous architect, facade engineered by one of the largest consultancies on the planet. 1 year after opening, an 80-kilogram piece of concrete cladding fell from this wall onto the pedestrian plaza below. Then it happened again. Now look at this one. 75,000 granite panels. Within a year, panels cracking, joints leaking, thousands of cladding elements replaced. And this, a brand new facade buckling in the sun. No structural damage, nothing broke, but the client is furious and the contractor is back on site. Every one of these failures has one thing in common. Somewhere in the chain, a load was wrong, or missing, or misunderstood. My name is Eugene Korch. I practice and teach facade engineering. And this video is about the loads that act on every facade and what happens when you get them wrong. Here is something that a surprising number of people on a construction project do not fully appreciate. A facade is not a passive skin, it is a structural assembly. It resists wind, it absorbs thermal movement, it deflects impact. It supports maintenance equipment, and it does all of this at once for decades, while keeping the building watertight. The facade does not carry building's load. The building frame carries floor loads, column loads, lateral forces, measured in hundreds of thousands of kilonewtons. A typical facade bracket carries 5 to 15 kilonewtons. The difference is at least a factor of 10. But the facade carries its own loads: dead load, wind, impact, barriers, thermal effects, seismic drift, snow and ice, maintenance access, and several more. For every project, the facade engineer must review the full list and decide which loads apply and which do not. Missing one can mean redesigning the facade after it is built, and redesigning a facade after it is built is one of the most expensive mistakes in construction. Wind is usually the dominant load on the facade. It determines the size of almost every structural element, and it behaves in ways that surprises most people. When wind hits a building head-on, it creates positive pressure on the front face. That is intuitive. What is less intuitive is what happens everywhere else. On the sides, the back, and especially at the corners, wind creates suction. It pulls the facade outward, and the suction at the corners is significantly stronger than the pressure on the front. Why? Because the wind detaches at the corners and accelerates. The faster it moves, the lower the pressure. Every fixing, every seal, every mechanical connection at the corner is being pulled outward, not pushed, pulled. And that is where facades fail first. Now here's something that catches people out during construction. A partially glazed building with an open loading bay on the windward side is temporarily a building with a very large opening. Wind pressure enters the building, adds to the suction on the opposite wall, and the net load on those panels increases dramatically. Panels that will be perfectly safe on a finished building can be at risk during construction when openings have not yet been sealed. The facade engineer must consider loads at every stage of the project, not just the completed building. One more thing about wind. The code divides the facade into zones, each with different pressure coefficient. Using the wrong coefficient for the wrong zone is common and serious error. And the difference between the corner zone and the center of the wall can be a factor of 2 or more. Same building, same wind, very different loads. Let me show you some more loads that get missed more often than they should. Dead load sounds simple. Everything has a weight. Add it up, but here's what actually happens on project. The design starts with double glazing. An acoustic consultant says the noise level is too high. The specification changes to triple glazing. Each additional pane adds roughly 2.5 kilograms per square meter per millimeter of thickness. On 30,000 square meter facade, that is a significant increase in total weight. If nobody goes back and updates the bracket calculation, the brackets are now carrying more than they were designed for. This happens more often than you would think. And this is not just design changes. A building is designed for specific loads in specific locations. An archive floor carries more weight per square meter than a standard office. When a tenant decides to swap those rooms around, move the filing into a space that was never designed for it, nobody on the facade team gets a phone call. But the slab deflects differently. The brackets are at the edge of that slab, and the facade feels every millimeter. Floor-to-ceiling glazing. If a person can reach it and push against it, that glass is a barrier. It must resist a horizontal load representing a person falling or leaning into it. The load depends on the building use. A residential corridor has one value. A nightclub balcony has a very different one. And the check is not a single calculation. It is 3 separate checks that do not act at the same time. A line load at the top, a distributed load across the infill, and the concentrated point load at the worst position. All 3 independently. The element must pass them all. Dark metal panels in direct sun. A black panel can reach 80 degrees when the air is only 35. That's surface temperature 60 or 70 degrees above the winter minimum. The panel tries to expand. If it is fixed at all four corners with no room to move, it buckles. This is oil canning, and it is almost always a thermal load that was not properly quantified, combined with fixing arrangement that did not allow free movement. And then there is one that most people outside facade engineering never have heard of. Let's look at sealed glass units. The cavity is sealed at specific temperature and pressure during manufacture. When temperature changes, the gas inside expands or contracts but has nowhere to go. This creates a real pressure on the glass from the inside the unit. If the unit is manufactured at sea level and installed at altitude, the lower external air pressure adds even more. This is a genuine load, not a movement, and the glass must be thick enough to resist it. And even if the glass does not crack, the bowing turns each unit into a curved mirror. The facade looks distorted. For the client, that can be just as much of a problem. This is only a 10-minute video, and we have only scratched the surface. If you want the full picture, every load type explained, worked examples, the complete wind calculation from the first principles, barrier checks, thermal range, and load combinations, we have a dedicated course on our website. The link is in the description. If there is one idea to take away from this video, it is this. Several items on the load list are not loads at all. They are movements: thermal expansion, seismic drift, wind-induced sway. The facade is designed to accommodate them through sliding connections and flexible joints. They only become loads when freedom runs out. A well-designed facade converts potential loads into harmless movement. The bracket slides, the joint opens, the gasket flexes. Nothing breaks. Get the movement strategy wrong, and those same movements become forces that can buckle panels, crack glass, and pull fixings out of the structure. That is the difference between a facade that lasts 60 years and the one fails in the first 5 years. Let me bring it back to where we started. An award-winning library with concrete falling onto the plaza, an opera house with thousands of panels replaced within a year, a dark facade buckling in afternoon sun. None of these buildings were designed by amateurs. None of them used cheap materials. Every one of them had a professional team, reputable contractors, and engineering consultancies behind them. The lesson is not that facades are fragile. The lesson is that loads are unforgiving. Every facade is structural assembly, resisting real forces every day for decades. Dead load, wind, thermal, impact, barrier, maintenance, and more. Miss one, underestimate one, or fail to update the calculation when the specification changes, and the facade will let you know. If you want to go deeper, the full course with 10 lectures, worked examples, and animations is linked below. See you there.